This episode is sponsored by Audible. It's possible that the reason we appear to be alone in this galaxy is because we're the first life forms to emerge here, but it's also possible that we're the first to re-emerge here. So today we are returning to our Fermi Paradox series to consider the idea of galactic disasters, natural or artificial events that might prevent life from developing or wipe out civilizations. If you are new to the Fermi Paradox, it is essentially the notion that the universe is a vast and ancient place, probably containing billions of planets with conditions parallel to early Earth, and thus we would expect to see a ton of intelligent life out there, but we don't seem to see any. This apparent paradox has many proposed solutions, and the one we'll examine is that something, or someone, might have killed off life in our galaxy at some point in the past, and that Earth is the first or among the first places where life has returned. So we'll be considering a number of potential galactic disasters today, and also some extragalactic, universal, and even multiversal disasters. Let's discuss first, what would it take to sterilize just a planet of all life? The most heat-resistant known lifeforms on Earth are microbes that can survive at 130 centigrade for no more than a couple of hours, but it's still rather tricky because there are microbes living down the deep ocean or caves where they might survive a whole planet's surface being scorched sterile. They could then repopulate a planet, and with quite a head start, since they already would have a lot of advancement on the early microbes that probably inhabited our planet 3 to 4 billion years ago. Though at the same time, if some disaster happened periodically, say every 100 million years, and that could account for most larger land animals like birds and mammals, that probably would have the same net effect of preventing any intelligent civilization from arising. It takes a long time to go from microbe or insect to high intelligence, so if you get crashed periodically back to only simple life forms surviving the ashes, the planet will remain empty of civilizations, even if it's only barren for a few decades every 100 million years or so. We always, in a Fermi Paradox solution context, need to consider if some proposed solution would be in every galaxy or just our own, because a strange or improbable event or chain of events might occur in one galaxy, but if it is not happening in neighboring ones, it does not work well as a Fermi Paradox solution. You can colonize between galaxies even without access to faster light travel, so a single galaxy solution explaining an absence of civilizations in the Milky Way isn't enough. If intelligence is common and old, someone would have colonized the Milky Way from Andromeda or some other galaxy by now. So for example, it's possible that life emerged in our galaxy 7 billion years ago, then some event caused a series of supernovae that wiped out all that life 4 billion years ago, and Earth was the first place it emerged after that. However, you still have civilizations in neighboring galaxies from planets billions of years older, who might have been out on the interstellar scene billions of years before us. With fast light travel, they should colonize their own galaxy and neighbors in mere thousands of years, but even without it, you should be able to get your own galaxy colonized in a few million years, and get your neighboring galaxies in at most a few tens of millions of years, not billions. Still, if it happens in one place naturally, then it might happen in other places, and of course supernovae are a fairly universal phenomenon. We don't know much about what supernovae near Earth do to our planet, nor can we assume the impact would be the same on other ones. For instance, our main concern for a supernova hitting us is that one that goes off within 25 light years or so of us could be energetic enough to critically damage our ozone layer on the half of the planet exposed to the blast. That is not a planet sterilizing event for Earth, but we did tend to assume it was for some time. We had to revise our models from the 1970s that had thought a supernova event 50 light years away might destroy 90% of our atmosphere for centuries, and now think the effects are much more mild and require higher proximity. Even in those older models though, it wasn't life-ending, but more in the asteroid impact or supervolcano scale of planetary disruption that recovers with a new ecology emerging. What actually happens if a supernova happens near Earth? Well, we've no eyewitness accounts, and even our geological record is rather flimsy in regard to supernova detection at the moment, but it does seem to happen periodically and mostly mildly. The volume of a sphere is proportional to the cube of the radius, so there is 8 times as much space within 50 light years than there is within 25, and 64 times as much within 100 light years. Out beyond that, they would still impact us, potentially rather severely in an ecological sense of disrupting the existing norm and leaving traces, but not in a planet-threatening way. Inside of that 25 light year radius, you are getting walloped by X-rays, gamma rays, and cosmic rays that are going to damage your ozone layer badly, exposing you to more intense ultraviolet till it recovers, causing a big uptick in cancer in animals, and wreaking even more havoc on many microbial life forms, especially those that need sunlight to live so can't be buried under protective layers of earth or water or whatever animal or plant they live in. Those charged particles coming in break diatomic nitrogen up into highly reactive nitrogen atoms that form nitric oxide and other nitrogen oxides, and those individually can destroy hundreds of triatomic oxygen or ozone molecules while they persist. The ozone layer would recover in a year or two, but for another decade or so you would be getting blasted by cosmic rays. This is not going to sterilize a planet. Life down in the deep sea or caves will continue, but if that event was happening every several million years, it's not hard to imagine it preventing complex life getting a foothold and getting big brains and spaceships. Fundamentally though, supernovae just are not common enough to do that to most planets in a galaxy, even if we accept the more severe side of the uncertainty of those models. Of course, some events could cause an uptick in star formation periodically, and stars capable of going supernova are short-lived, so that can result in a wave of supernova several million years later, as all those bigger stars formed in that wave of stellar formation start dying in short succession. Still, even though supernovae are often described as the most powerful and destructive events in space, they are just not powerful enough to explain a perpetual galaxy-wide kill-off. We have a unit called the FOE, in which we measure supernovae energy release, and it is 10 to the 44th joules. Now this is a huge amount of energy. This is a billion times more energy than our own sun releases in any given second, and comparable to all the energy it will emit in its lifetime. However, if we think of this in the context of Einstein's E = mc squared, it's only about the energy release of 10 to the 27 kilograms of matter, and around a 2,000th the mass energy of our Sun, a single solar mass. And Type 2 supernovae are of stars more than a dozen times as big as our Sun, so a FOE is about half the mass energy of just Jupiter. Energy release in terms of its destructive potential in space falls off with the square of distance, so if a supernova could critically damage our atmosphere at 25 light-years, one 10 times farther away would need to be 100 times more powerful to do the same. We happen to be 1,000 times further away from that from our galactic core, for instance, so a blast there would need to be 1,000 squared or 1,000,000 times more energetic to have the same effect, but in this case it would be a galaxy-wide one. Of course, that would require about 1,000,000 times the mass energy, or 10 to 33 kilograms, 500 solar masses, and the largest stars are not even a tenth of that mass and do not convert anything like all their mass into a supernova blast. Even hypernovae, the most powerful recorded supernovae events, aren't recorded at more than 10 to 100 times the normal supernovae release. Antimatter, which on encountering normal matter releases both its energy, would be far worse than a star exploding. Just an example, it is entirely possible there are many other universes out there, and that half of those are principally composed of antimatter rather than regular matter. In certain types of cosmology, these parallel universes could collide or interact in some fashion. If, for instance, a wormhole opened up and an anti-Jupiter emerged through it, it could collide with another large planet or star, and emit the equivalent of about 4 FOE, a fairly strong supernova, and indeed possibly a good deal more, as antimatter would tend to catalyze fusion too. See our antimatter episode for details. If an anti-star came through, that would be 1,000 times more powerful and out of record volume of space a couple 100,000 times bigger than a normal supernovae, though that would still be a relatively tiny corner of a galaxy. Needless to say, an anti-galaxy sliding through would create a protracted collision with some galaxy releasing 1,000,000 billion times more energy than a supernova, and that sort of event could keep an entire region of the universe thoroughly cooked for millions of years after the energy blast reached a given piece of it, traveling at light speed. And this would only be considering a small exchange of matter between a universe fundamentally the same as our own, just with antimatter dominant. We'll come back to some other cross-universe disaster scenarios later. A moment ago I mentioned the energy needed to have a near-Earth supernova effect that took place 1,000 times further away at our galactic core. I did not pick the galactic core on a whim though, or just because it is central to a galaxy and we are discussing galactic disasters. Very few processes can fully convert mass into energy, so that there's no matter left and you get that full E = mc squared yield, or even a decent fraction of it. Hydrogen fusion in stars generally stays under 1% for instance, and often well under, since most stars, especially big ones, never burn more than a tenth of their hydrogen fuel. But a black hole can do way better, which is one reason we often suggest them as a power source for advanced civilizations. The destructive power of black holes tends to be badly misrepresented in science fiction. Natural black holes tend to form in highly destructive events, but black holes by themselves are not particularly destructive. If our sun magically turned into one tomorrow, it would kill us, but not by crushing us or tearing us apart. We would die simply because we no longer were getting sunlight. That black hole sun would only be a few kilometers across, not a million like the sun is, and you could get much closer to it safely than you could a normal star because it has the same gravity as before, but it isn't giving off scorching amounts of radiation. Very little matter would fall into one as it is tiny in cross-section compared to a planet or star, and anything not on a straight intercept trajectory would simply fall into orbit around it. What happens though is that a lot of matter would slowly drift nearby and fall into various orbits of that black hole. As more and more gets added, we get a lot of occasional collisions and decaying orbits, picking up gravitational energy and forming an accretion disk that emits a lot of energy in the deadly X-ray and gamma ranges. Those near the event horizon are essentially picking up their mass energy in kinetic energy that can come off in those dangerous bands of radiation. When you dump matter down to a black hole, it can't escape once it is over the event horizon, but on the way down it will pick up tremendous speed, and if it's colliding with stuff before crossing the event horizon, those collisions are releasing amounts of energy not much short of what antimatter would, and they radiate that as heat energy principally in the X-ray band. Planets can also have an accretion disk. This is pretty parallel to a planetary ring like Saturn's, but the energy levels are much lower and would show up in the infrared band. A black hole with a binary companion that it starts to consume is going to release far more energy than a supernova, but rather gradually over a period of around 1 million years, not in a quick blast like a supernova. However, the centers of many galaxies are home to very large black holes that often contain several million solar masses. They presumably ate at an average rate of 1 solar mass a millennium, or Jupiter mass per year. Indeed, quasars, the brightest objects in the universe, which we believe to be such galactic core supermassive black holes actively consuming matter and releasing energy, generally do so at a rate of around 10 to the 39 watts of power, or a Jupiter's worth of mass energy every few days, with the brightest doing as much as 100 times that, or a Jupiter mass per hour. That is essentially a perpetual supernova going off at your galactic core, and while that power is very spread out by the time it would reach a planet as far from the core as Earth is, it is also a constant, prolonged effect. Now, even though a quasar might be 100 trillion times brighter than our sun, and in the nasty gamma ray zone for a lot of it, this is not actually that bright in terms of light on a planet, because of that sheer distance involved. It would be more luminous than our full moon, but still only around 1% of the sun's light. Still, all that constant bombardment of high-energy radiation and particles could easily strip a planet's entire atmosphere away after thousands of years. What's more, we have an effect called a quasar wind or a quasar tsunami of superheated relativistic gas that can pulse out around a galaxy as a massive shockwave, disrupting the whole galaxy's normal star formation rate. So galaxies with quasars in them are not likely to be hospitable to life. The good news is that quasars are mostly gone these days. We can only still see them because they are so bright we can see the ones far away in space and thus far back in time. The nearest known quasar is Hani's Vorwarp, which is actually an extinct quasar, one which ran out of a large amount of new gas and matter to eat. This recently extinct quasar is about 730 million light-years away and appears to have gone extinct maybe 70,000 years before that light we now see left that quasar, and has been cooling down since. The nearest active quasar is 1.7 billion light-years away, much older. Quasars are artifacts of an earlier and more collision-heavy period of the universe, peaking about 10 billion years ago, and they have been getting rarer as time goes on, but they are believed to pop up in weaker form occasionally during galactic mergers. They aren't likely to be a concern for us, but the Milky Way may have been a quasar at some point in the past, as might many galaxies. Past disasters, even those billions of years back, are obviously of great interest to us in regards to the Fermi Paradox though, since if a galaxy was a quasar 5 billion years ago, then it probably wasn't full of life then, even if it had been before. Indeed, any galaxies that have a supermassive black hole at their core probably have had many phases with an active galactic nuclei, a period where it is absorbing a large amount of matter. Now, a quasar is an active galactic nucleus, but the reverse is not true. This swallowing of gas or stars at the core is not a steady flow in general and can vary a lot in intensity. The periods where a very great deal of mass enters one in a relatively short period is a quasar. The period when a fairly large amount of mass goes in is just an active nucleus, and this is probably a phase most galaxies like ours go through fairly often. A Seaford Galaxy, which is about 10% of those we see, is essentially the same process as a quasar, only far less powerful, with the core only being about as bright as the rest of the galaxy combined, as opposed to hundreds of times brighter, and is a type of active galactic nuclei. But these are still protracted events, very powerful and very long. You can have shorter bursts of much higher power like a gamma ray burst or GRB, which are about 1,000 times more powerful than your average quasar, and the most powerful recorded was 1,000 times more powerful than that, and around 1 billion times more powerful than the Sun's typical luminosity. Since these are short affairs of milliseconds to hours, not centuries or millions of years, we are very unclear on both their mechanism of production and rate of occurrence, and indeed it's likely there are several different mechanisms ranging from hypernovae to a star getting eaten by a black hole in a short swallow, particularly something like a white dwarf or neutron star, which are much more compact and whose remaining matter is much more gravitationally bound to them, so not prone to leaking prior to getting gulped or tidally disrupted, which might then happen over a mere few seconds. GRBs are nasty affairs and typically come as more concentrated polar blasts than big spherical detonations, and we still know little of them, so they are a plausible candidate for regular galaxy-spanning ruin, though this would still be more of an issue of frequency than strength, since no single GRB would sterilize a galaxy even though its destructive blast or cone is much bigger than a supernova. We do have one thing even more powerful than a GRB, and that's a black hole merger. Though this energy release is far larger, it is a gravitational radiation, so it isn't wrecking atmospheres like high-energy gamma radiation or ionized particles would, though it has been suggested that two shock fronts of gravitational waves, say from two black hole mergers in a relatively small region of space and time, might meet and form new singularities or micro black holes, which would be short-lived and bang off in black hole evaporation events. We've also only observed fairly mundane black hole merging thus far, those in the tens of solar masses region. Presumably during a galactic merger event it is possible for a pair of supermassive black holes to merge, what we call ring down, with far more energetic results, and regardless, galactic mergers are pretty galaxy disrupting events too. Though it should be noted that our galaxy is a terrible cannibal suspected of eating over a dozen others, and some are still partially extant. We always say Andromeda is the closest galaxy and on a collision course with us in a few billion years, but we will amend that to include the two Magellanic Clouds, smaller galaxies orbiting the Milky Way, nearly to the point of overlapping. But at last count, there are 59 small galaxies closer to us than Andromeda, eaten remnants or tiny satellite galaxies. As I've often mentioned on the show in terms of intergalactic colonization, there is plenty of junk between major galaxies to serve as waypoints. It's not just a couple million light years of nothing and no stars. These sorts of galactic consumption events, while stretching over billions of years, are one of the many things that could disrupt the core of a galaxy to feed fresh waves of matter into that core black hole and make it an active galactic nucleus for a while. Such natural galaxy-wide disasters could be the reason we don't see older civilizations, and indeed we believe they are a big factor in making the universe inhospitable to life for maybe the first half of its existence. But that would still be billions of years before our planet formed, and a civilization that came from a planet just 10 million years older than ours and evolved at the same rate as us would probably have colonized the whole galaxy by now. Or for that matter, a civilization from a planet that formed at the same time as Earth, but where life evolved just 1% faster than us, would have a 20 million year head start on us. Of course, a civilization that much more advanced could cause a galaxy-wide disaster, accidentally or otherwise. We don't know what kind of technologies might be possible for us in the future, of course. We might develop some capacity to poke into other universes with antimatter as the dominant matter there, or different physical laws with destructive effects if they spilled into ours. We've no idea what would happen if we cut a wormhole into a four-dimensional universe and that extra dimensionality overlapped into us, for instance. And indeed, as we discussed in our episode on parallel universes, some cosmological models like string or brain theory predict universes or brains colliding periodically. However, just inside known physical laws, there's a lot of room for galaxy-wrecking accidents or intentional damage. There is a theoretical device known as a Nico Dyson beam that's essentially a Death Star. You convert an entire star into a weapon by wrapping it in mirrors and lenses and pointing at something you want thoroughly dead. Our sun is nowhere near the brightest, some are 1,000,000 times brighter, but if we made our sun into such a device, it could burn out the whole crust of a planet down to the mantle in the time it took for that planet to spin around once, and only that long because you would need to keep the beam on it till the planet spun around. The nastier version of this instead used that light to push on mirror-backed missiles with lasers, what we call a relativistic kill missile or RKM, so that you can simply time a volley of such missiles to arrive in one big blast, or spread out over a day and thus only need to apply enough energy to torch the surface. A single such device can purge an entire galaxy of hospitable planets and keep doing it over and over again. Indeed, it could do it in many neighboring galaxies, and there's no reason it need be built around your own sun, in favor of a bigger, brighter one, or in favor of converting many thousands of stars into these weapon platforms. After all, our galaxy contains hundreds of billions of stars, so converting just a fraction of a percent of them into these gives you millions of them, and enough to eradicate planets throughout an entire galactic supercluster. Of course, such devices need guidance systems and the ability to detect and alter course a bit to hit a planet, especially across the galaxy, and you might instead use smart machines to go to those planets and simply dismantle them too. Variations on Grey Goo, tiny little machines that simply build more of themselves till they convert everything into themselves, or berserker probes, big or smaller machines that go someplace and annihilate it via onboard weapons, or simply parking nearby and building more of themselves or doomsday weapons, are something that someone might intentionally build, but could also be created on accident. You might create terraforming Von Neumann probes or Grey Goo designed to turn entire solar systems into Dyson swarms for future colonists, and have that mutate in design or intent with disastrous results. We see an example of this in Alastair Reynolds' Revelation Space series, where Von Neumann terraforming machines, the Greenfly, meant to create trillions of plant-rich habitats around a star, run amok turning everything into such habitats, so that stars turned green with the only light reflected away being those bouncing off green leaves. Such a thing is not just a threat to your own galaxy, but everywhere else, spreading out at relativistic speed as it encounters new construction materials, and spawns new fleets to reach new stars and new galaxies, as fast as their starship drives could take them. Though if you are focused on eradicating life and quick, you probably go the RKM route. The RKM is much faster than Grey Goo approaches since no need to slow down is required. You are literally ramming a planet, or a star for that matter. Hypothetically, two large and relativistic objects could be shot at a star to hit it from both sides and plow down to the center, causing a shockwave and detonation. You could also artificially be producing most of the effects we discussed today, only in more timed and controlled fashions, and we looked at various ways to weaponize black holes in our episode Weaponizing Black Holes. As usual in regard to galaxy-spanning disasters of an artificial and intentional variety, it does beg the question of why the civilization doing it didn't just colonize the whole galaxy instead of blowing it up, but there are some scenarios where they might opt to do that, and we looked at those in our episode Fermi Paradox Sleeping Giants, like being so xenophobic that they don't even want to colonize, because the colonies would be mutant strains of themselves they would want to wipe out too. Accidents though are more likely, in terms of the galaxy we see now, one apparently uncolonized but in which we exist, and exist many billions of years after it would seem plausible civilization should have arisen if life was prone to popping up on Earth-like planets, and evolving to intelligence rather than being something less common than winning the lottery. You are not likely to eradicate your galaxy on accident under known physics, but there's unknown physics presumably, and we do have some theories for things like false vacuum, and accidentally destroying space-time by puncturing it and basically draining reality away. But that wouldn't leave us around unless it was a sort of effect that only destroyed a limited region, and was something that tended to be done accidentally by basically every species once they reached a certain point. Amusingly, a lot of our candidates for fast light travel have some scenarios for that sort of thing. FTL tends to be intrinsically linked to time travel, and it's possible that time travel would tend to wipe a civilization out simply by employing it, via scenarios like the self-consistency principle, and see our time travel episode for details. You might turn on an FTL device and delete your civilization backwards in time. Another thing often overlooked with FTL concepts is the huge amounts of energies involved. A highly relativistic missile, massing just as much as an ICBM, is coming in with a destructive potential on par with the asteroid that killed the dinosaurs, and an ultra-relativistic skyscraper-sized RKM is the sort of thing that would rip the whole crust off a planet. However, in science fiction, folks tend to ignore that those big spaceships, massing about that much and moving faster, should presumably be far worse if they impacted. After all, it takes infinite energy to get any piece of mass up to even light speed, let alone faster. But even the hypothetical and fictional FTL devices that play with warping spacetime rather than endless and impossible acceleration tend to be energy gluttons comparable to RKMs or more. Remember what I said earlier about if two gravitational radiation shock fronts collided, the possibility of many micro black holes briefly forming and rapidly evaporating explosively. Those are warping spacetime, and if you are doing the same artificially by warp drives or wormholes, you might get effects like that. Wormholes are extreme curvatures of space-time much like black holes, which would tend to involve lots of gravitational waves. Gravitational waves propagate at light speed, so two systems opening something like that up, a pair of wormholes or some other space-time twisting gate, might blow themselves up some decades later when the waves meet those coming from another distant gate. While science fiction often shows folks disrupting wormholes or other space gates to prevent an invasion, and theoretical wormholes can be disrupted or broken by dumping too much matter into them, the effect is likely to be very, very explosive even in astronomical terms. You do not blow up the incoming fleet, you blow up the solar system, that sort of thing. Needless to say, that all relies on highly speculative physics, but it is plausible that folks trying to bust out of the constraints of known physics might succeed, but only briefly, and with galaxy-spanning results. Even some scientists on the Manhattan Project discussed, and placed bets on, the possibility that the unnatural event they were forcing might create some hyperstable pocket of spacetime or form of matter around which the rest of the universe might collapse. In science fiction, we often see ambitious experiments at the ragged edges of a species' understanding of science, with grand results that turn out to be far more revealing than anticipated. Some scientific civilizations out there might find this out firsthand, and the hard way, as might everyone else in their galaxy, or their universe. It is possible that the solution to the Fermi Paradox is not that life is all that rare, but that every time a galactic firstborn civilization arises, it turns itself into the last. Science fiction has shown us a lot of catastrophes on the galaxy level or even wider. Some of the classics include Larry Niven's Known Space series or Alastair Reynolds' Revelation Space, or Thanos and his Gauntlet from Marvel Comics, but perhaps the greatest of these comes from the Grand Master of science fiction himself, Isaac Asimov, and his 1972 novel The Gods Themselves. I don't want to spoil the novel with any discussion, but it is often considered Asimov's best standalone novel, and it won the Nebula Award for Best Novel, the Hugo Award for Best Novel, and the Locus Award for Best Novel. I'll also toss my own recommendation in there by giving it the SFIA Audiobook of the Month. Asimov's skill as an author needs no elaboration, and the audiobook is wonderfully narrated by Scott Brick, one of my favorite narrators, and it is available from Audible. Audible has literally got centuries worth of audiobooks if you need to escape away during these troubling times, but they also have tons of non-fiction, news and fitness programs, podcasts, and other original audio shows. However, in response to the crisis, they've launched stories.audible.com, a collection of free books available to anyone, focused on younger audiences to help out parents and teachers. In addition, there's a lot of sci-fi classics up there like Frankenstein and A Brave New World, so make sure to check those out. As an avid audiobook listener since I was a kid, I can testify what a great option they can be for getting kids into reading, and again, it's free. The content is available in several languages from your computer, smartphone, or tablet, and there's no ads, no sign-up or login, just click, stream, and listen. Of course, Audible's normal inventory can still be accessed for a 30-day free trial, and Audible members not only get discounts on any audiobooks they buy, but a free book every month. Additionally, they are now giving unlimited access to their Audible originals. You can start listening today with a 30-day Audible free trial. Just visit the link in the episode description, audible.com/Isaac, or text Isaac to 500-500. So next week we'll be taking a look at future types of governments, both variations on modern ones that might occur with new technology like artificial intelligence, and how some old ones might re-emerge as we move into space colonization. Then we'll finish up the month of August with our monthly livestream Q&A on Sunday, August 30th at 4 p.m. Eastern Time, and you can join us then to get your questions answered. We'll then head into September and start the month out with a look at space nomads and nomadic fleet-based civilizations. Then in 3 weeks we'll move on to part 2 of our new series, Becoming an Interplanetary Species, as we look at colonizing cislunar space and the Lagrange points. If you want alerts when those and other episodes come out, make sure to subscribe to the channel. If you'd like to help support future episodes, you can donate to us on Patreon or on our website, isaacarthur.net, which are linked in the episode description below, along with all of our various social media forums, where you can get updates and chat with others about the concepts in the episodes and many other futuristic ideas. Until next time, thanks for watching and have a great week.